So, what's our initial hypothesis? So we have a function u in W1P, omega is in R2, into R2, and it satisfies this differential inclusion. Almost everywhere, right? And we have the following useful facts. So if A is a conformal matrix, then if we form the conformal matrix in 2 by 2, it happens to be itself again. And for any smooth function W, then this is just a generally true fact. The divergence of the cofactor matrix is itself. Sorry, the divergence of the cofactor matrix is 0. And for any Sobolev function g, there exists Gn belong to C infinity. Again, let's not do that because I'll get called out on it. So let's just say W1P omega, C infinity omega, such that G minus Gn in the W1P norm goes down to 0, so long as the boundary is nice enough. Oops, nice. Okay, so these were the things we noted, and let's try and put them together. So our aim is to show that we have that the coordinates of this function weakly are harmonic, right? And the first claim is that we can have a weak version of this for any Sobolev function. So the way I've written this requires a smooth function because we're differentiating the derivative. So let's call this thing star. So claim for any, let's say, W tilde belonging to W1P, omega containing Rn into Rn, then omega satisfies star weakly. And what does that mean? That means we don't have this in a pointwise sense. We have this in the sense that when we test it, when we test it by integrating against a smooth function, then the identity is still true. That's what we mean by the statement, the thing holds weakly. We abandon the pointwise notion. We go to the averaged notion via testing against smooth tensor function. So what happens if we test this thing pointwise? Let's get the weak form. So i.e., if we tested this thing, let's put it over here, with a smooth test function, so if this held true pointwise, then it's certainly true that the divergence of the cofactor of the gradient of W times the test function is equal to 0 if it's true pointwise, right? Because we're just integrating something that's 0. And this is something with compact support inside omega, so we can integrate by parts and put the gradient on the omega. Yeah? Now we have to be careful because this means divergence of each row, right? So to make that a little bit clearer, I'm going to put the divergence of I'm going to put the square brackets and then an index to indicate which row. So divergence like this of the kth row times this function equals 0, where this thing indicates kth row. Okay, so it looks like I need more space from that. So once we have that, from this thing we can just integrate by parts, and then we're going to have that the cofactor of dw, kth row of that, dot product this thing is equal to 0 for all x, for all phi, which is of compact support. It's a scalar function. We take the derivative as a vector. We dot product that n vector with the n vector. That's the kth row of this thing. That's equal to 0 for k is equal to 1, 2, n. And then this thing is what we call the weak form of the equation. Okay? So this thing is the weak form. In the sense of, let's call that star, 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 star. Okay, so why is that true? Well, from this little calculation, if we have a smooth solution, yeah, then obviously it satisfies it in the weak form. Yeah. So we are going to take our function like this, our Sobolev function, and we're going to take the sequence that approximates it. Yeah. So let w tilde n belong to C infinity, omega into Rn, such that w tilde minus w tilde n w1p, omega tends down to 0. And then we have that the gradients converge strongly in LP, right? So if we look at this expression, the expression we want to be equal to 0 for our function, then, as Josh was saying, we can apply the triangle inequality and simply control the difference between that thing and the approximating sequence. So notice the following, that integral of the cofactor of dw tilde, the kth row, dot product to test function. I can subtract one of the approximating sequence here, and that'll just be 0, but let me just put it in. All right, and then this thing is less than, let's maybe do it like this. Let's put the absolute values inside. The cofactor of the w tilde, oops, the kth row, minus the cofactor of the w tilde n, the kth row, like this, and then this guy, this test function, dx, yeah? And then we can just apply Holder's inequality, because what is this? This is just a vector created out of individual components of these derivatives, yeah? Because the cofactor matrix is, or at least when we're doing this in 2 by 2, let's maybe do this in 2 by 2 and make life simple. The cofactor matrix is just this thing which has individual entries in terms of other entries of the matrix of the derivatives. Yeah. So this thing has to tend to 0 in LP. Yeah. Everybody happy with this? In higher dimension, then the cofactor matrix is this product of partial coordinates, and then we have to think about what p we require in order to be able to control that. But we're doing this in the simplest way, it's just 2 by 2, so any p bigger than 1 is fine, or any p equal to 1 or bigger is fine. Because this thing is just a C infinity function. We can even bound it just by its sup norm. Yeah? Yeah? So, this is less than, let's just take the sup norm of this guy, make life super easy. And then just the distance between this and its approximating sequence in LP omega, and then this thing goes to 0 as n goes to infinity. Yeah? And this thing, again, is just equal to 0 because that is our identity, right? That is this identity that we're given up here. So this thing, we can just forget about it. It's just equal to 0, yeah? And then this thing doesn't depend on n, right? But this thing gets as small as we like as n goes to infinity, therefore this thing is equal to 0. Are you all with me here? Thumbs up if that makes sense. Yeah? Cool. Thank you for pointing out this typos. Definitely made it make no sense. All right, everybody good? Yeah, so we do have the claim established that this W does satisfy the weak version of this identity. Yeah? And then it's kind of straightforward because, so, for almost every x belonging to omega, we have that this guy, if the gradient exists, it's conformal, right? So being conformal, it is the case that when we do this thing, we take the conformal matrix of the u of x, it is equal to this thing. Yeah? So the weak form from star star, the weak form, we have that actually the integral of the gradient of x, where we take the kth component dot product this thing, is equal to 0 for all phi belonging to compact support like this. Yeah, I should emphasize this is true for all compact support omega. Yeah, cool. And this is exactly saying that each component of W, oh, it shouldn't be W, it should be U, each component of U is weakly harmonic, right? Because what is the first row of this thing? It is UK, comma 1, UK, comma 2. Yeah? That's the first row. So, which is the same as the gradient of UK, the kth component of U. Yeah? So, and that is exactly the statement of being weakly harmonic. If we could, if this was smooth and we could integrate by parts, that would say that the harmonic, the Laplacian applied to UK times the test function equals 0, right? That's exactly the weak form. Yeah? Everybody with me? And that is what I told you was the hypothesis for Wales' lemma. And it's either YL or LY, and I never remember which one. I think that might be it. Wales' lemma. Implies that, therefore, U is C infinity and harmonic. So once it's C infinity from this, it's actually harmonic. Because once it's C infinity, then testing it, putting the derivative on the other side, means that we have equals 0 for all test functions, and since this is smooth itself, the only way that can possibly be true if it's pointwise equal to 0. Yeah? So the weak solution of a PDE, the Laplacian, turns into the smooth solution. So we have something that a priori we don't even know that the second derivative exists, and we can't formulate the PDE pointwise, but we would cover that it actually does exist. And we started with a hypothesis that we just have one Sobolev gradient satisfying the differential inclusion, and that was enough to boost us into this situation where we have the actual derivative being smooth, all derivatives exist, and we have the good stuff. You know, we have the regularity claimed. Yeah? And you might think, okay, well, a lot of the work was down to Wales' lemma, and that's true. And Wales' lemma is pretty easy. Well, I want to say super easy, but it is relatively elementary to prove. And it is so nice that I am unable to resist giving you a little bit about it. But I'm going to go faster because I want to get to other stuff. So this is going to make more sense to those of you who've done some Sobolev space. And if you're not one of those people and this doesn't make sense, you're going to have to look at this and think about it a little bit afterwards, or just trust me on this little sketch of the reason. So how does Wales' lemma work? Well, actually, let me call it theorem. That weakly harmonic becomes strongly harmonic. Well, we use this stuff about convolution that I talked about before. So remember I said when we convolve something, it's morally the same as taking an average, except we take the average over something which is a little bit smoother, right? So I said if we take the average literally, it's like integrating against something which is a characteristic function of a ball. And all we're doing when we convolve is that we take something a little bit smoother like this, which just rounds off the corners, right? But what's the property of the average? If we have the characteristic function of a ball divided by the volume, then we integrate it, it's got integral 1, right? So we're going to try and mimic that. So we're going to take phi, which has got compact support, let's support it just inside the ball of radius 1. Like this. We want it to have integral equal to 1. So this is integral in whatever dimension we're in. Yeah. And we want it to kind of look more and more like the characteristic function of a small ball. So we're going to rescale it in the following way. So if we do this in dimension n, we're going to do it like this. This, then epsilon to the minus n. And if we do this, so I think of this as being what phi is. If we rescale the x like this, then that makes the support be something of size basically epsilon, right? Because if the support was originally of size 1, then if we move more than epsilon away from 0, then it's 0. So this thing puts us in something of size support inside a ball of radius epsilon. This thing blows up the function by epsilon to the minus n. But if we're in n dimensions, then the volume of a ball is epsilon to the n. Volume of an n of a ball of radius epsilon is roughly epsilon to the n, right? So this thing will indeed have the right properties. So again, I write nonsense. We define this thing is equal to the rescaling like this. Okay, and that's just kind of motivation, but you can just check by change of variables that this thing still has the property that this thing has got integral equal to 1, and that's not hard. But it should also be sort of clear from these pictures. All right, so that is going to be our substitute for integrating over a ball of radius epsilon. So morally is it's not a small morally. The characteristic function of the ball of radius epsilon over epsilon to the minus n. That's what it is, yeah? Times whatever normalizing constant to make it equal to 1. I don't know what it is, say gamma of n, the volume of the ball of radius 1 to make this equal to 1. Okay, so when we convolve, what we do is the following thing. So we take our function u and we, do we call it u? Let's call it something else. Let's call it w again because we just used u. So we're going to write this thing, and that's defined to be as follows. We're going to integrate w of, say, y, rho of y minus x dy, okay? And that thing, if we had just the characteristic function of a ball of radius epsilon divided by the volume of a ball of radius epsilon, that thing would be exactly just the average of the function w around the ball of radius epsilon centered on x. That's all it would be. Yeah? And instead we have this slightly smoothed out version of it. Yeah? And what's cool about this is that we can now take all the derivatives we want, because if we take a derivative, it now lands on this thing, this smooth test function. Yeah, it lands on the smooth test function. Yeah. So that means that if we have a Sobolev function, we can take a derivative, it'll land on this thing, but then we can integrate by parts and put it back onto this thing. Okay, we can put it back onto this thing. So if w belongs to w1p of omega, then the gradient of this thing will, after an integration by parts, be the same as this thing. So the gradient will actually be the average of the gradient as well. Right? This is true for the function, just in one line, but it's also true of the gradient. And this is why you can expect that these convolutions are going to tend closer and closer in the LP norm to the actual function. Okay? For the reason I did motivation, that we're just smearing things out a little bit. Yeah? So these guys will indeed do this cool thing. They will converge stronger, more and more strongly in Sobolev space to the actual function. Yeah? Cool. So how does Weyl lemma work? So we have something that is weakly solving the harmonic equation. So we have this. Like this. Yeah, that is our first step. Now, our claim is that, oops, this is equal to 0 for all phi of the compact support omega. Now, our claim is that when we do this for the convolutions, we also have that this thing will be harmonic. So the convolutions will be harmonic, but this time they will be smooth harmonic. And that follows because when we take the divergence of the gradient of this guy, when it's in this form, then that thing will be the same as this thing dot product the gradient of this thing. So Laplacian of, let's just write the W epsilon equals the convolved function with the kernel like this. So this thing will be equal to, so I'm swapping D and this thing for the gradients, which I guess I shouldn't do, but anyway, they're equivalent. Then this thing will turn out to be this thing. Which is just a calculation, because this thing is the gradient dot, the divergence of the gradient of this guy, right? So if you're taking the divergence of this guy, then the derivative initially hits onto this thing, which gives you this thing. And I've missed out the rho epsilon here. So a little calculation will convince you of this. Okay? But then this is exactly the hypothesis of being weakly harmonic, so this thing is equal to 0. So for free, the convolutions are instantly harmonic. Okay? Cool. So convolutions being harmonic mean that they satisfy the mean value property. So mean value property W epsilon of x is the average around a ball of radius r of x of W of epsilon, whatever, dh1 of s, like this. Okay. That's because these things are harmonic. Yeah? But these guys tend in a strong sense to the actual function. Yeah? So for almost every x, this is not a consequence of the LP convergence, but it's also true just by the fact that W is an LP function. It satisfies the Lebesgue point property. So for almost every x, this thing is tending pointwise to W of x. So this is tending pointwise to W of x, and this is tending to W of x in an LP sense, so it's also true for almost all radii. So this implies that W of x actually satisfies the mean value property. Whatever variable I said, let's use y, let's use z. Okay? That's also true. Little exercise, check for yourself that this is the case. Yeah? And if this is the case, then assuming our function that we chose is radially symmetric, so that means that, so in the case of R2, we can just rotate it and it looks the same, right? We rotate it around the origin. Then when we take our convolved function like this, using the Carré formula, just breaking this down, the integral into the integral around the various radii, because this thing won't change around the radii, we'll just be averaging this thing. This means, oops, this is for this guy, I mean for the function itself. So around the radii, if this thing is radius symmetric, around the radius of the ball of radius r around x, and this thing is just constant, it's just like one of these values here. So we will just be averaging this thing, or taking the integral of this thing, because this is just a constant, and then by the mean value property, that's equal to the perimeter of the circle times the central value, which means that ultimately from this, you'll have that the convolved functions are actually equal to the function itself. Okay. So if rho is radially symmetric. Now this is faster than I've done all the other explanations, and to really believe this, you're going to have to write this out yourself. But these are all the components. These are all the things you need to know. We just take the convolved function, yeah? We check that we can write the derivative like this, because we integrate by parts and end up averaging over the derivative. Yeah? Calculation, take the Laplacian of the smooth function. That's the same as divergence of the gradient, which can be written like this when we differentiate through the integral sign. And that's exactly the weak form of the Laplace equation, so that's equal to 0. Therefore, each one of these W epsilon are themselves harmonic, therefore they satisfy the mean value property. And by strong convergence onto W, this means this is true for almost every x, and for almost every radius. And then this means that the function is equal to its own convolution, and therefore it's C infinity. Okay? This is a very good exercise to learn the properties of convolution, to be convinced of the properties of convolution. And it's also an excellent exercise to do that, because the payoff is big. You see Weyls' lemma, and Weyls' lemma is a kind of a little hint as to a lot of good stuff, because one of the main ideas one of the main purposes of Sobolev functions is to solve PDEs and to solve them weakly. So our strategy was to use the information we have to be able to have some equation in the weak form, and then use properties of the equation itself to go from the weak form to the strong form to the pointwise form. And that is that's the story of modern elliptic PDE. That this is the mind-changing advance in regularity of elliptic PDE. That instead of working very hard with specific equations to try and show existence of classical solutions, you can rather easily show the existence of weak solutions, either by a variational principle or by just some thing like Ree's representation theorem, some function analysis type thing. And from that, you get a weak solution, and the properties of that weak solution will allow you to, in many, many cases, bump up to a strong solution. So you end up having a classical solution in any case. So this was an absolutely huge innovation because, this just makes many theorems that existed beforehand a special case of this general machine. So the machine is that you give up on the notion of strong solution, you accept a weak solution. You can get a weak solution by a relatively easy methods, and then you use the properties of the weak solution, just like we did in little sketch proof of Wales' lemma, to actually say that the weak solution is a strong solution. So this is the chess sacrifice I mentioned before. So for maybe hundreds of years, people were fighting to keep strong solutions and prove things in strong solutions because they think, what's the physical meaning of a weak solution? What do we do? What can we possibly do with something where we don't know that the derivative is actually there everywhere? That's of no use to us. But once you are willing to accept this notion of weak solution and this notion of weak derivative, then you can get some kind of a solution, a weak solution. You do the chess sacrifice of weakening what you're willing to accept. But having done that sacrifice, you're now in a stronger position because you actually have a notion of solution. And from that stronger position, you can use those properties to actually get a pointwise solution back, right? Just like in a chess sacrifice, you sacrifice your rook for a better position, and then you still get the checkmate in the end because your position is stronger. That's exactly what this notion is. The sacrifice puts you in such a better strategic position that you can recover the win, even though you seem to have lost a lot of information when you give up on strong solutions. All right, that is that. So the reason I did this was to motivate the next paper, which is, or the paper we've already discussed to some extent, which is Sverak's paper on Tardis conjecture, which has a very strong generalization of this. So, theorem. Again, it's Sverak. Notice that all the papers I suggested to you have Sverak as a co-author, and that's not coincidence. As I mentioned, he writes very neat, clever papers where there's such a neat idea that many technical complications are taken away. So some of these theorems, or the theorems I'm proposing to you, are all very distinct, powerful theorems, but with very short, neat proofs. So Sverak, 93. Now we're going to do a differential inclusion into a set K, into the 2x2 matrices, and it's going to have no rank 1 connections. It's going to be connected. It's going to be a submanifold, and it's also going to be elliptic in a certain sense. So suppose K is contained within 2x2 matrices. It is a connected submanifold. It is no rank 1 connections. Let me just write it because it's important. And it's elliptic. okay, in the sense that if M belongs to K and Tm denotes the tangent space to the submanifold at M, then given Lipschitz U such that so actually just let me add that it's going from omega into R2 such that the U of X belongs to K almost everywhere, connected, let's do C infinity submanifold, then U is C infinity. So we recover the regularity of the submanifold in the function that satisfies this differential inclusion, right? So before, we did the special case. So K is equal to these conformal matrices is the special case, right? Because this thing is actually a linear space itself. It's an exercise to see it has no rank 1 connections. So therefore, it satisfies the hypothesis of being a submanifold, having no rank connections, and also being elliptic because it is its own tangent space at every point. Okay. Yeah. So this is a special case. So in a sense, the Sobolev generalization of the first theorem of complex analysis, that just having a derivative in the space of conformal matrices implies C infinity regularity. This is taking Sverak's theorem for K equals the conformal matrices. But obviously there are many more sets that satisfy these hypotheses. These hypotheses are not that specific. There are many, many examples of things that satisfy this. Okay, cool. And has no rank 1 connections. I think I might have said it, but I got too excited about this and I didn't actually write it down. No rank 1 connections. Yeah. So if this is your submanifold, then you take the tangent in every space, T of M, and you want this thing to have no rank 1 connections. Okay. Cool. Everybody happy? Yeah. So, in a sense, it's a far-reaching generalization of a theorem related to the first theorem of complex analysis. Yeah? And it only holds true in 2 by 2. Very little is known about differential inclusions into higher dimensions, about regularity of them. But there is this phenomenon, this general phenomenon, that if you have a differential inclusion into a set with nice enough properties, then you get instantly much higher regularity. And hopefully you guys can see straight away that if we don't have the hypothesis having no rank 1 connections, then it's false, right? So note, if A comma B belongs to K and then the rank of A minus B is equal to 1, then we can do this function that we did before, this so-called laminate function like this, A, B, A, B, A, B, right? And then this thing is a perfectly nice Lipschitz function, but in no sense is this smooth because the gradient is discontinuously jumping, right? Yeah? So there's no hope that this thing could possibly be true if there's a rank 1 connection inside our set. Yeah? But if this is ruled out and there's also no rank connection inside the tangent space, then the theorem is actually true. And this is the same paper that proved, that has this theorem about compactness, that if you have a set K that is connected inside 2 by 2, that is closed, that has no rank connections, doesn't have to be elliptic this time, then simply having a sequence of gradients that are LP close to that set means that those gradients have to converge strongly. Yeah? Yeah? So the ideas for this proof and the compactness are quite related, and that's one of the papers that you have to choose. All right, so I'm going to now discontinuously jump. Well, we'll connect these things. No, it's not discontinuous in many ways. But what I'm going to do now is stop talking about differential inclusions, approximate differential inclusions. We're going to talk about quasi-regular mappings, quasi-conformal mappings, the generalization of holomorphic mappings, and then I'm going to state the final theorem of the 3 papers that I want you to consider. I want you to choose reading from, and then I'm going to go back and start to develop the theory to get to some weaker version of that theorem, and start to prove the many properties of quasi-regular and quasi-conformal mappings. Okay, so taking a step back, what we learned from Liouville's theorem is that there is no higher dimensional complex analysis in the sense of forming a differential inclusion into the conformal matrices, right? So Liouville says no theory, or no interesting theory of differential inclusions du of x belonging to the conformal matrices for n bigger than or equal to 3, because there is just basically one example, the inversion to the sphere or an affine mapping, or the inversion to the sphere times the reflection times an affine mapping. So what properties how could we possibly generalize this? So consider this. So let's start where we do have an interesting theory. So if n equals 2, there's an extremely rich theory. This is a course you all did. This is exactly complex analysis, right? If we take U is from omega inside the complex numbers into the complex numbers, holomorphic, so by a one-time differentiable, then, let's call it F, because I want to write Cauchy-Riemann equations. Then F of x plus iy equals u of x, y plus iv, xy, satisfies Cauchy-Riemann equations. I mean, we've done this before. Cauchy-Riemann, so u of x, I've talked about it lots of times before. X, so define f tilde xy to be u of xy, v of xy. In other words, we turn this function from the complex numbers to a function from R2 to R2. Then this thing satisfies this differential inclusion. Once again, belongs to conformal matrices 2 by 2. So pick any, say, xy inside whatever, inside our new region. Let's call the new region. So we're turning this complex region into a real region in an obvious way. So pick xy into this thing. Then consider the image of the gradient f tilde x comma y acting on the unit ball b1 of 0. Well, let's just write b1. So again, if the ball has no thing saying where it's centered on 0. Then this thing, what is this? What is the shape of the image of the ball acted on by the gradient itself? What is it? So this is the unit ball. We are just taking a fixed gradient and we're acting on all the vectors in the unit ball with this fixed gradient. What am I going to draw here for the image? Come on. Right, it's got to be either a smaller or a bigger ball. There's nothing else it could be, right? It is also a ball. Just let's use exactly your words. Is a smaller or bigger ball? Yeah? Cool. Now, let's try and weaken this hypothesis by not insisting that the shape of this thing gets sent to a ball, but it gets sent to something that is not too far from a ball in the sense that it isn't going to be too thin an ellipse or too fat an ellipse, right? So in 2 by 2, it's relatively easy to describe that. We want the thinnest width to be not too much. Let me express this better. We want the longest width divided by the thinnest width to be not too big a constant, right? That would be a way to express that the ellipse isn't too long and thin. Now, in high dimensions, that's not quite as good, quite as easy a thing to do, but let's take this instead. So to insist on matrices or matrix. So I'm running out of time. Leave whenever you want. I want to complete to a certain, get to a certain specific thing. So insist on a matrix A that does not send balls to things too far from a ball. Then we could do the following. We could say, let's take A acting on a ball like this, and then let's consider the image of it. This is A on the unit ball, okay? And then we can consider the volume of the image, yeah? And also consider the smallest ball that contains the image, okay? And what we'd like is that the smallest ball, or the volume of the smallest ball that contains the image, divided by the image is not too big a number. Yeah? Because if we have a thin ellipse, then this area can be quite small, right? While the ball that contains this can be quite big, comparatively, right? So this thing maps the ball onto the image of the ball like this, yeah? And then if we want that, so what's the volume of the image of the ball? Well, that's just the determinant of the matrix, right? So we want that the determinant, let's write this in capitals, that the determinant of A, yeah, is not too small compared to the volume of the smallest ball that contains it. And what's the smallest ball that contains it? Well, if we take the operating norm of the matrix, right, that will be the longest length it can be. Yeah, that'll be the radius of the smallest ball that can contain it. Yeah, yeah. So we want the determinant to be bigger than some factor, some constant of the actual operating norm to the power n, which is the volume of the ball that can contain this image. Yeah? For some small c0. That would be a way to prescribe that the gradient is not sending things to two small ellipses, right? It doesn't constrain the size in any way, right? We can have a huge ellipse or a very tiny ellipse, but we don't want the ellipse to be too squashed in and thin. Yeah? Do you guys agree this is a reasonable condition? Yeah? So that's the same as saying that a to the n is less than c0 to the minus 1 of determinant of a. Yeah? And then we're going to let q be c0 to the minus 1. Yeah? So if we have a function which is in w1p omega in Rn into Rn, and okay, I'm going to write p to begin with, and then we're going to see what p has to be. And we have that this identity holds true, that when we take the operator norm to the n, this is bounded by q times the determinant of this thing to the n. So implicitly, we want the determinant to be positive in this definition. Yeah? Then this is what we're going to call a quasi-regular mapping. Q quasi-regular. But if you think about it, what we want to do is integrate the derivative in nearly everything we do, right? And this thing is a product of n partials. This thing is also the power to the n. All these norms are equivalent. So if we have p less than n, then we can't integrate these expressions, and it becomes a useless thing, right? Or a priori, it's a useless thing. So it turns out we can actually do a bit less than n. But let's start by just saying we have this in n, so that we are in a position to integrate these guys. Okay? And if q equals 1, then what happens? Well, if q equals 1, that's the same as c0 being 1, right? And that would mean that the volume of the image of the ball is the same as the volume of the smallest ball that contains it. Yeah? If q equals 1, right? Because look, this thing is always an inequality, right? But if q equals 1, then it has then we cannot have these like bits here that are left behind, right? We can't have these excess parts here if q equals 1, right? Because if we had these excess parts, then the determinant would be strictly smaller than this thing. Yeah? The determinant would be strictly smaller than this thing. Do you see what I mean? Thumbs up if you see what I mean. Let's try again. So if we had q equals 1, then what does it mean? Then it means that the volume of the smallest ball containing the image is less than equal to determinant, right? Since we always have equality, it actually has, we always have this inequality just from this picture. So it actually means that the volume of the smallest ball containing the image of the ball is the same as the determinant. Yeah? So if the volume of the smallest ball containing the image of the ball is the same as the image of the ball, then there is no excess parts here, and then therefore the image of the ball is a ball. Right? Right, I'll give you an answer in a second. So let me write the statement. So if q equals 1, then du of the image of the ball is a ball. Yeah, and when you learned about determinants and images, you probably, you did see this, I guess, for a square or a cube, but it is just generally true this is change of variables formula, right? So, for example, if this is the change of variables formula, if we have that the integral of any set A, determinant of du, dx, right? Assuming u is an invertible mapping, that is the same thing as this thing. Yeah? Just take, so in the normal change of variables formula, then you'd have this, right? You'll have determinant du of, I don't know, yeah. All right. So because of polar decomposition, you can decompose a matrix into an orthogonal matrix and then a positive definite matrix, positive definite symmetric matrix, and then the symmetric matrix you can diagonalize. So for a diagonal matrix, if you just consider a cube, then you can just see straight away that the determinant formula is true, and that's why people tend to talk about that in terms of cube, but it's just generally true. Or more geometrically, you can just decompose things into cubes and everything will be true, right? If you have a ball, then cut it into cubes, all the volumes of cubes are preserved, blah, blah, blah. I mean, that's just the proof of this, basically. Yeah? Cool. So we do indeed have this stuff that the determinant of matrix A is the volume of this ellipse. Yeah? And if it's equal to the volume of the smallest ball containing it, then it has to be the ball. Yeah? Cool. So that means when Q equals 1, we are back to conformal matrices, right? Then du belongs to the conformal matrices. Because the only thing that will send a ball to a ball, no matter what ball, is going to be a conformal matrix. Yeah? So this thing is a generalization of the theory of the theory of differential inclusions into the conformal mapping, i.e. of complex analysis in 2×2. Yeah? Yeah? But when we let Q be bigger than 1, then we're allowing some sort of distortion of the space, of the image of the ball, right? And that is a much wider class of mappings. And in particular, when n is bigger than 2, then we have a rich class of mappings that satisfy this. So there are many mappings that satisfy this, and they come up in lots of areas. And we can prove some analogs of the main terms of complex analysis for these things, these quasi-regular, quasi-conformal mappings. Quasi-conformal means that they're invertible as well as satisfying this condition. And that is where most of the course will be going from this point on. We're going to develop the theory of mappings that satisfy this kind of thing. And first in 2×2, by introducing methods from harmonic analysis, single integrals, and then we'll talk a bit about n by n. And this will be one of the main topics of the course. All right. Everybody happy? Yeah. All right. Perfect. I will see you all on Wednesday. Have a great day.